Hello, welcome back to the second course in physics. And now we will be talking about a different topic than in the previous lectures. And this topic is concerned with the effects of the motion of charges. So it's not anymore electrostatics in a way. It deals with electric currents in a way. So the contents of this lecture, we will start with an introduction as usual, and then we will define the electric current and derive the formula for the current which is associated with the drift of charge in a conducting medium. And then we will talk about the density of charge carriers in metals, especially as conducting medium. And we derive the different fundamental motions and velocities of the charges inside the carrier. We will talk then about the conservation of electric current as it passes through conductors. Then we will define the resistance of the current carriers. We will then move to the microscopic discussion of the process of the conduction in a current conducting medium. And then we will arrive at Ohm's law, set up this important law. And we will, in that sense, we will define the microscopic form of Ohm's law. And we will define the macroscopic form of this law. Then we will be discussing and talking about the materials as they carry current, whether they are ohmic or non-ohmic materials. After that, we will define a property of the material, which is the resistivity of the material. And we will see how this resistivity is affected by temperature. It is temperature dependent. So we will discuss the temperature dependence of this resistivity. And then we will mention or address the units of resistivity and the conductivity of material. So in the beginning, we start by mentioning that if two conductors are at different potentials, then upon connecting these two conductors with a conductor, then current will flow, charge will flow from one conductor at the higher potential. Positive charge will flow from the higher potential to the lower potential, or electrons will flow from the lower potential to the higher potential. And this flow of charges is the so-called current. And the current keeps flowing from one conductor to the other until the two are at the same potential. At that point, when the two become at the same potential, then current stops. There is no more force that can be applied to move charges from one to the other. Now, the problem of the flow of current is actually manifested by the lack of a potential difference source between two objects. So the problem is how to maintain two bodies at two different potentials. That was originally the problem. And that's how the problem that people faced in maintaining a current between two objects at two different voltages. And this problem was solved by the invention of the voltaic cell by Alessandro Volta in 1800. So this invention provided us with the means of maintaining a potential difference between two conducting bodies, and maintaining the potential difference between these two allows the continuous flow of current from one to the other, and this opened a new field for new discoveries in the field of electricity. So this was the invention of voltaic cell is really a turning point in the field of the dynamical process and the motion of the charges and the associated phenomena. Volta, the prominent scientist, has demonstrated that dissimilar conductors, two dissimilar conductors, like for example copper on the one hand and zinc on the other hand, or carbon on the one hand and zinc on the other hand. These two dissimilar conductors, if they are placed in contact with any conducting liquid, like for example salt water, water in which salt is dissolved, these two dissimilar conductors exhibit a potential difference between them. So this is a demonstration by Volta during his work, and when these two electrodes or bodies placed in the electrolyte in a solution, if these two electrodes, the so-called electrodes, are externally connected by a conductor like a wire, for example, a conducting wire, then a current is maintained in that wire, in that conducting wire. So this was a method of maintaining a current by means of using two dissimilar conductors immersed in a conducting liquid or an electrolyte. And that was the starting point of the work on the electric currents, actually, because that was the necessary step to maintain a current in a circuit in order to start the work in that field. And that was by the invention of the voltaic cell by the prominent scientist Alessandro Volta. The charge carriers, when we talk about the flow of charges due to the difference in potential between two bodies, the charge carriers, we have to mention that they are not of the same kind. They differ with the material of which the conducting object is made of. So, for example, in conductors, the charge carriers, the carriers which carry the current, which carry the drift of charge from one point to another, the charge carriers are electrons. In electrolytes or solutions, conductive solutions, the charge carriers are ions. And in semiconductors like silicon or so, the charge carriers are holes. So in each case, when we maintain two ends of a conducting material, current flows, and those are the types of charge carriers that carry the current from one end to the other of the conducting object. So now, if we consider a region in space containing particles, charged particles of charge plus q, each particle having a charge plus q. And if we consider that in that region of space of interest, the number density of these charges is n charges per unit volume, in that case, an electric field in the region, if we apply an electric field to that region which contains these charges, this electric field will exert force on the charges and will drive the charges parallel to the electric field if the charges are positive, of course, and they are assumed to be positive. The electric field applied to these charges will drift these charges with a drift velocity, we call it v as a vector. And the direction of the drift velocity is the same as the direction of the electric field in the case of the positive charges. And this figure shows the cylindrical shape of space with the charges inside, and these charges are drifting with velocity v, and this is parallel to the electric field. And the charge dq that is contained in this cylinder that we show in the figure, the length of the cylinder is simply v, the drift velocity, times dt. dt is the time interval that we select. We select a period of time dt that is very small. And so this is the length of the cylinder, and the cross-sectional area of the cylinder is S. That means the total charge enclosed in there is equal to Q, which is the charge per unit particle, times the number density, the number of particles per unit volume, N, times the volume. The volume is simply the cross-sectional area S dot the height V dt. So that gives the total charge enclosed in this selected volume of space. And then now we define the current as the first derivative of the charge dq by dt. It's the rate of change of the charge crossing a given cross-sectional area of the conductor. I is equal to dq by dt, and this is equal to the number density n times the charge of a particle q times the velocity, the drift velocity of the particles, dot the surface area, the cross-sectional area of the conducting wire. And from this definition of the current, we can define the current density, which is the current per unit area of the cross-section of the conducting wire. J, the current density, if assumed to be a vector, and looking at the definition of the current above in the first equation above, then J would be simply N, the number density, times Q times V. This definition of the current density allows us to calculate the current by saying that the current is equal to simply the current density J times the cross-sectional area if the current density is uniform. So if the current density is uniform, the current I is equal to J, the current density, times the cross-sectional area, which is perpendicular to the current density, which means J dot S simply. And if the current density is not uniform, then the current is not obtained by simply J dot S, but rather we define DI, the current element of current, in a given area, small area. We section the cross-section S into small areas, And J dot ds is the current through that element of area, ds, and then we can integrate or add J dot ds in order to obtain the total current across the cross-sectional area. The unit of electric current is the ampere, where from the definition 1 ampere is equal to 1 coulomb, a unit of charge divided by unit of time, or the symbol of ampere is simply A, and the symbol of coulomb is C, as we have mentioned before, and that of the time is small s, second. So 1A, 1 amp is equal to 1 coulomb per second. That is the unit of current. And now the charge carriers in metal, taking into consideration these formulae that we have just arrived at, that we have defined, and we take into consideration the typical number density of the charge carriers in a metal, of electrons in a metal, the typical number is simply n equals 10 to the 28 electrons per meter cube. Any typical metal will contain that many electrons per meter cube of its volume. And accordingly, if we substitute this number density in the previously obtained formula and take into consideration typical cross-sectional areas and so on of the wire, of the conducting wire, like 1 millimeter square or so, we obtain a drift velocity as a consequence of the application of the electric field of 10 to the minus 4 meter per second. That is the drift velocity of the charge as we apply the electric field across the conducting wire. It's some sort of an average velocity of charge, of the flow of charge across the conductor. And we have to remember that if we consider the free motion of the electron between the atoms as it moves, it scatters from atoms, and if we consider the path of the electron as it moves from one scattering center with atom to another scattering center with another atom, the velocity, the random velocity of these electrons is about 10 to the 6, 1 million meter, that is 1 million meter per second, which is much, much higher than the drift velocity. So when we talk about the drift velocity as a consequence of the application of the electric field, it's not actually this random velocity which is associated with the random motion of the electrons inside the material. The random motion of the electrons inside the material with the absence of an applied electric field, although the velocity in magnitude is very high, it's like 1 million meter per second, but the total effect of this random velocity is zero because it's simply random. It's just like the motion, the random motion of the gas in this room, for example. It goes randomly back and forth, but the total effect is zero. There is no drift of the flow. There's no drift of the fluid from one point to another in space. And the only way that we can obtain such a transport, such a motion of the charge from one point to another is by the application of the electric field, which will introduce a drift velocity, although it is very much smaller than the random velocity associated with the electrons, but it is responsible for the transport of charge through the conductor. And now we consider the case where if the electrons or if the current, the charge carriers, whatever they are, if they are moving across a conductor, and then the conductor splits into two parts or more at a junction, then we know that if this system is isolated, there is no extra charge that can be created, and no charge can be annihilated. Thus, we have a conservation of charge. And that conservation of charge dictates that the current I naught should equal to the current I1 plus the current I2. The current entering a junction should equal to the total current leaving the junction, and taking into consideration that the current is simply the J dot ds integrated over the surface area. J dot ds is equal to the current if we convert the surface integral into a volume integral. J dot ds is equal to div j d tau over the volume of the junction. Then the total current I naught minus I1 minus I2, if that's the total current, if we take the div j d tau, which is j dot ds, which is equal to 0, then the conservation of charge dictates that div j is equal to 0 at any junction. This is a consequence of the conservation of charge. And now we define a new parameter, which is the resistance relevant to the current and the electrical phenomena. And in this sense, we mentioned that if a potential difference V is applied between the two ends of a conducting rod or wire, this potential difference between the two ends of the conductor will result in a flow of current I, as we mentioned. And the resistance of that rod to the flow of current is defined as R, resistance, is equal to the potential difference between the two ends of the rod divided by the current flowing in that rod. This is the definition of the resistance. So it's some sort of a frictional resistance to the flow of current under the application of the electric field. The unit of the resistance is called ohm. That is the unit of resistance, where 1 ohm is equal to 1 volt per ampere. That's from the definition. And in symbols, ohm is symbolized by the symbol omicron, capital Omicron, omega. 1 ohm is equal to 1 volt per ampere. And now we move to discuss on a microscopic level the conduction process and how is current created and the relevant issues. One of the first pioneers who have worked on the conduction in metals is Paul Drude. In 1900, Paul Drude have assumed that the ions in a metal are fixed, and the current is transported through a conducting metal rod by the motion of the free electrons or the mobile electrons, which move between the ion cores, causing the flow of current. And this model is called the free electron model. So upon the application of an electric field between 2 points of a conductor, what carries the electric current, what makes the electric current pass through that conductor, is simply the motion of the free electrons, where the positive charge the positive ions are fixed in the metal. They do not contribute to the current flow. The electrons, if we look at them closely, the electrons move in rapid and random motion between successive collisions with the ions. So an electron would be moving in space between the ion cores in the metal, and once it gets to the region of one atom, it scatters from that atom and keeps moving until it encounters another atom, and it scatters from it and moves in a straight line again until it scatters from another atom, and so on. So in general, the motion of the electrons between the ion cores is like random. And the distance that the electron travels between one scattering center, or one atom where it scatters, and the other scattering center, this distance varies, of course, between the first scattering process and the second scattering process. But we can always define an average length of path that the electron moves before it encounters scattering. And this definition would lead to the definition of an average time, because we have these electrons move with a certain velocity, characteristic of the material, of course. And since it has a velocity, the definition of the average length or path that it moves between one scattering and the other would also lead to the definition of an average time, which is the mean free time. The length, the average length, is called the mean free length, and the time, the average time, is called the mean free time between two scattering processes or centers. So this is on a microscopic level how the motion of the electrons occur inside the metal. Collisions between electrons are being ignored in this process, as you notice, because we only consider the collisions with atoms, and that's because the electrons are very small in size relative to the atom. So considering that the electron is about 10 to the minus 5, the radius of the electron is about 10 to the minus 5 that of the atom, then the cross-sectional area, or the probability for scattering of an electron from another electron is extremely small relative to the probability of scattering of electron from an atom. It's extremely small, so we ignore it in our discussion. The average time, as we mentioned, between two collisions with the ions is tau, which is the mean free time. It's the average time that is taken by the electron between two collisions, as we just mentioned a little while ago. And an applied field, accordingly, an applied field results in an average drift velocity of the electrons in an opposite direction to the field, because the electrons are negative in sign. The charge of the electrons is negative. So the average velocity due to the application of the electric field is simply the force exerted on the electrons, which is E times the electric charge times the electric field, divided by the mass that defines the acceleration, times the average time, mean free time, the average time that it takes between the two scatterings, tau, and this, the acceleration times the time, defines the average velocity. So this defines the average drift velocity of the electrons due to the application of the electric field. And accordingly, the current density can be derived from this formula, because we know previously that the current density is simply n, the number density of the charge carriers, times the charge of the particle, which is minus e, that's why we have the minus sign, times the velocity. So if we consider that the velocity is the average drift velocity, then we are considering the average current density within a cross-sectional area, and substituting for the drift velocity that we have just arrived at, then the current density is simply n times e square, the e is the electronic charge square, divided by the mass of the electron times the mean free time between two scattering processes times the electric field strength, E. Thus, we notice that J is proportional, linearly proportional to the electric field. And this is a formula that is correlating the current density with the electric field. And now we are ready by this definition and by these results, we are ready to define Ohm's law. And Ohm's law in a microscopic form, the microscopic form of Ohm's law as we have just derived it is J is equal to a parameter, a constant that is dependent on the material we call sigma times E, because J is linearly proportional, as we just noticed, linearly proportional to the electric field. And the constant of proportionality is sigma, the conductivity of the material, and that sigma is equal to the value of n times e squared times tau over me. Notice that this quantity, the conductivity, is dependent on the material, because n, for one thing, is the number density of charge carriers in the material, and this is a characteristic property of the material itself. Now, the electronic charge E square is fixed for all materials. It's simply the charge of the electron, doesn't change. The number density changes, the mean free time tau changes from one material to another. Actually, it even changes from one body to another of the same material. If the material is prepared well, if it's very good crystalline structure, if it's not, if it has impurities or not, tau, the mean free time, changes even from one body to another of the same material. So it's a material characteristic. And me is the electronic mass. It doesn't change. So through the change in the number density of the charge carriers n and the change in tau, sigma changes from one object to another, depending on the material and how pure or how well prepared is that material. That is the so-called conductivity. And this J equals sigma E is the microscopic form of Ohm's law. So let's consider now a homogeneous conductor of length L and cross-sectional area S carrying a uniform current density J. Then in this case, the total current is equal to simply the current density J times the cross-sectional area S, which is simply equals sigma E, that's using Ohm's law, times S, which is simply sigma, and we substitute for E by V over L, the voltage difference between the two, the top and the bottom part of this conductor, times the cross-sectional area S, and thus we arrive at the formula V is equal to L over sigma, the conductivity, times S, the surface area, cross-sectional area, times the current. Or if we write, instead of 1 over sigma, if we write rho, then V is equal to rho L over S times R, where rho is 1 over sigma. Or we can rewrite it. Notice that this relation is a linear relation between the voltage drop between across the ends of the conductor and the current flowing in the conductor, and the proportionality constant is called R, the resistance R, and this is simply rho, which is the resistivity. It's the inverse of the conductivity of the material. It is the resistivity of the material, rho, times the length of the conductor divided by the cross-sectional area of the conductor. So this quantity R depends on the material and the geometrical factor of how the body, the object, the conductor is made. So this is another relation that relates the voltage across a conductor and the current flowing in that conductor, and where R, the resistance of the conductor, is simply equals rho, the resistivity of the material, times L, the length of the conductor, divided by the cross-sectional area in meters square. And this relation shows that the current is proportional to the voltage, or vice versa. They are linearly related. These materials that hold this relation true are called ohmic materials, where the voltage and current are linearly related through Ohm's law. And in this case, for the ohmic materials, V and I, as this figure shows, they form a straight line. The relation is a straight line between V and I, and the slope of that straight line is simply the resistance R. But not all materials are ohmic. We have non-ohmic materials, and in this case, the relation between V and I is not linear. And this is the case for example, in the case of electrolytes, or in the case of vacuum tubes, or something like that. So there are some materials that are non-ohmic. Not all materials are ohmic. And we have mentioned a little while ago the parameter rho, the resistivity, and now we address this in a little bit more details, and we recall that the resistivity is simply 1 over sigma, and which is equal to the mass of the electron divided by the number density of the electrons per unit volume, divided by the electronic charge square, divided by the mean free time between the two collisions. So this, on a microscopic scale, this defines the resistivity of the material, which is again a material property. A material property depends on the number density and the average time between two scattering centers. So this quantity, the resistivity, is characteristic, as we mentioned, of the material. And this quantity, the resistivity, is some sort of a frictional resistance to the flow of current. It's like the frictional resistance of a surface as we move an object across the surface. It's that kind of resistance, or like the kind of resistance of an object if it's thrown in water to move in a water. It faces some sort of resistance, like a frictional resistance somehow. And this quantity is temperature dependent. It's not constant at all temperatures. The resistivity is temperature dependent, but the dependence on temperature is very slow in a sense. So it does not vary much with temperature. And the formula that gives the temperature dependence is simply rho is equal to rho naught times parentheses 1 plus alpha t, where rho naught is the resistivity of the material at 0 degrees centigrade. So if we set up this definition, rho naught is at 0 degrees centigrade, and alpha is the constant of proportionality. Thus, T is the temperature of the conductor in degrees centigrade. This gives the relation. The temperature coefficient of resistance alpha is characteristic of the material. So it's like positive for all metals. Alpha is always positive, which means that all metals, their resistivity increases with increasing temperature. But alpha is negative for some materials, like, for example, electrolytes, or like carbon, or like silicon, which are semiconductors. So in some materials, their resistivity drops with the increase in temperature, but not metals. Metals, their resistivity increases always. And here we show a figure that illustrates the resistivity as a function of temperature. So, for example, we notice that the constant, what we call alpha, is not really constant over all temperatures. And that's why the curve is not really linear with temperature. It curves because alpha is a constant quantity at very small temperatures near the 0 centigrade. So these figures illustrate that, for example, for iron, the resistivity starts increasing linearly in the beginning, and then it starts curving because alpha changes with temperature. Alpha for iron near 0 degrees centigrade is 0.005 in Kelvin to the -1. And in the case of copper, it's much better because it's a more free electron model. Copper is a more free electron, it obeys more the free electron model. So it's more linear somehow, and the constant of proportionality alpha is 0.004, and it is positive. The resistivity increases. And we notice that for carbon, for example, the factor alpha is minus 0.0005, which means that the resistivity is dropping with temperature. And the units of resistivity and conductivity, the SI units of resistivity are ohm times meter by the definition of the resistivity. And the units of conductivity, sigma, is 1 over that quantity, which is 1 over ohm, 1 over meter, or ohm to the -1, meter to the -1. Ohm to the -1 is typically sometimes called mho, the reverse of ohm per meter. And at this point, I would like to finish this lecture, and I thank you for your attention.